So just some quick terminology, just so that we're on the same page of what things are. First of all, a program. So we've all heard program a lot. Basically, the formal definition of a program is that it's instructions for the computer to perform a specific task. So the program tells the computer what to do. Software is what programs are commonly referred to. So software is basically just a program. And then a programmer or software developer is someone that creates and tests computer programs. So programmers work in nearly every industry. Programmers work in industries that you wouldn't really think they do, like they work in business, medicine, government, law enforcement, agriculture, academia, entertainment, engineering. I don't know how engineering didn't make it onto that list. Especially in engineering, you're going to be writing code. I think 20 years ago, someone could sneak through engineering without knowing how to code. That's not true anymore. And it's pretty much every single engineering job I've had to know how to code. And if you don't know how, they just tell you to go figure it out. So taking this class now is going to make things a lot easier. It's also going to help you get hired, because if you have C++ or MATLAB or Python or whatever on your resume, that's going to put you ahead of someone who doesn't have that. So scientific and engineering side of programming, scientific computing. So this is where you would model the buildings or model I don't know, like mechanical parts. This is often called scientific computing, and this is basically computing that or code that solves engineering problems using numerical methods. So this would be solving differential equations with numerical methods. And some of the more common methods are the finite element method and finite difference methods. So most of the software packages that you'll use, like SolidWorks, these are finite element codes that solve differential equations. So they might solve, say, the heat equation to calculate heat flow through something, or they might solve like the Navier-Stokes equation to calculate fluid flow through a system. So these, and you can imagine that, like, if we can take, like, say, the building you're thinking about building, if you can model that with code, that's going to be a lot cheaper than trying it out and having it fail. This is one reason why pretty much everything has moved towards computer modeling, because it's a lot cheaper to model things numerically than it is to try, like, build something in the lab and try it and see. And even fields that you wouldn't think about, like biology, usually you think about biologists, they go out and collect samples and they're studying like deer migration or habitats or whatever. All of that is being modeled numerically now too. And so even in those fields, people need to know how to program. And it's because it's a lot cheaper. Writing code is cheaper than going out and doing a month-long research study collecting things. So that's, plus the other nice thing about the scientific computing is we can model things for a lot longer than we can run an experiment. So for instance, I've worked on code that was modeling oil and gas wells for like 100-year timeline to see if the cement in them would fail. And we can't go out and do an experiment for 100 years. I mean, we could, but by the time we got results, it would be the next like 5 generations down, and so it's not very practical. So we can model things out like years and years and years by running code that might take like a day to run. So it's actually really cool what people are doing with this scientific computing. So just some more terminology. We pretty much all know like the components of a computer. So computers have what's called a CPU, so it's the central processing unit, and they have a main memory, which is the RAM. And then we need some way to get information into the computer, so that would be the input devices, so like the keyboard, scanner, camera, joystick. So anything that we can use to get information into a computer would be considered an input device. And then output devices are things like screen, printer, speakers. And then we also have the secondary storage devices. So these are things like the hard drive or a USB drive. So the central processing unit, this is basically the brain of the computer. This is what runs the computer. Your computer couldn't run any programs without the CPU. And so I don't know if you guys have heard of ENIAC. That's the world's first programmable computer. And it was basically one big CPU. And it was 8 feet tall, 100 feet long, and it weighed 30 tons. So if you compare the size of that computer, 8 feet tall, 100 feet long, 30 tons, to CPUs that we have now, their CPUs now are basically small chips. I mean, we've gone from a computer that's like that big, like 30 tons, to a computer that basically fits in our phones are basically a computer now. So it's pretty incredible how far the technology has progressed in like such a short amount of time. Main memory, this is basically the computer's working area. This is memory that is used while you're running programs. So it's where programs store data and where programs are run, and it's volatile. So we know that if we turn off a computer and we don't have our stuff saved to the hard drive, it's going to lose that data. So the main memory is erased when the program terminates or when the computer is turned off. This is also called random access memory, or RAM. And this is stored in chips on the computer. And the reason why we use this is because it's quicker to access than memory on the disk drive. So if you've ever tried to run like an operating system from a hard drive, you'll know why we use RAM to run, say, an operating system or to run our programs. So the main memory is organized into these storage locations called bytes. And one byte can store a letter or a small number. And we're going to spend some more time talking specifically about how data is stored in these bytes. So right now this is just kind of an overview of this. But most computers have millions to billions of bytes. So like if you hear like a hard drive has like 60 gigabytes, that's like 10 to the 9th bytes of data. And then each byte is divided into 8 storage locations known as bits. So each byte has 8 bits. And a bit is the smallest piece of memory that you can have. And this is a 0 or a 1 is stored in each bit. So each byte has 8 bits, and each bit has a 0 or a 1 stored in that bit. The bytes are organized as 8 consecutive bits, and each byte has an address. Let's say this is our memory, and so each one of these numbers are addresses. So that 0 would be an address, 1 is an address, 2 is an address, and each one of those addresses has a byte, which is a consecutive arrangement of 8 bits. So each one of these addresses represents a byte with 8 bits. So if we look at this memory, we look at address number 16, that has 149 stored in that byte. And if we look at address number 23, that has 72 stored in that byte. So this is just a really rough overview of how things are stored on a computer. If you take the computer architecture class later on, you'll learn a lot more about this. Software. We know that everything the computer does is controlled by software. We wouldn't be able to do a lot on a computer without software. Software, remember, is a program. That's what tells our computer what to do. And so the system software that we normally have with a computer is the operating system, obviously. And this is the operating system controls the computer's hardware, manages devices, and allows programs to run on the computer. Utility programs, these are like virus scanners, data backup programs, and then software development tools. And so software development tools we're going to be learning some software development in this class and how to use some of these tools.